this video, we're going to talk about a one sample t-interval for a population mean. So I'll read through the problem and I'll explain my work. I have already worked through it beforehand to try and speed up and shorten this video a tad. So if you do want to try this problem, you could pause it, see if you get the same result as me, and check your work along the way. So here we go. A couple of AP Stats students wanted to know the average amount of sprinkles that are on Tony's Donuts. The group collected a random sample of donuts and counted the sprinkles on the donut. Here are the number of sprinkles for their random sample of 12 donuts. So they picked 12 donuts randomly at Tony's Donuts and counted the number of sprinkles. That's their raw data right there. What we need to do is we need to construct and interpret a 95% confidence interval for the mean number of sprinkles on donuts. So the general idea here is these students want to know, of all donuts that Tony's Donuts produces with sprinkles on them, what is the average number of sprinkles that they put on each donut? So they want to know for all donut, not just for the 12 that they picked. So we are doing a confidence interval here. Giveaway is in the question right there. So the acronym that we're using to keep ourselves organized is PANIC, which means we need to write down the parameter first, then go through assumptions, name what type of interval we're doing, actually do the interval, and then provide some context and wrap things up there. So I've already done these pieces. I'll explain them along the way. So since we are dealing with means, I started with mu is my parameter, mu. So mu is the mean number of sprinkles on donuts. The purpose here is I'm just defining what is the thing that we're trying to estimate. What is the variable we're trying to estimate in the context of the problem? So we're trying to predict what is mu, which is the mean number of sprinkles on donuts. Now, before I can actually do this interval and do this problem, I need to check the assumptions. If the assumptions aren't all working out, the problem essentially falls apart. We can't actually do it. So I'm checking the assumptions next to make sure, can I actually do this? So for a one sample t-interval, which is what we are doing, the three assumptions are independence 10% and check whether our sample size is large enough. So for checking independence, it's really these first two together. We're making sure the sample of 12 donuts were randomly selected. So when I went back and read the problem, yes, the sample of 12 was randomly selected. That's going to help us with independence. The next thing, we're checking what I'd like to call the 10% assumption, which is my sample needs to be less than 10% of the population, meaning I don't want my sample to be too big. So my 12 donuts, yeah, that's going to be less than 10% of all donuts that Tony's Donuts makes. So the independence and 10%, they're working together really to accomplish independence, okay? The third condition assumption is what I'm going to spend a little bit more time on. I need to check whether the sample size is greater than or equal to 30, basically checking, is my sample large enough? For this particular problem, my sample size is 12. So I said the sample not large enough, so we check box plot. If your sample is greater than or equal to 30, you are set, okay? You are set. The central limit theorem, which I've referenced sometimes, is what is at work there. So if your sample is large enough, we know things are going to be all right with our sample and therefore everything else. So if your sample size is large enough, we're golden. We're good to go, move on. If your sample size is not bigger than 30, there is a little bit more we can do. What we need to do is we need to take our raw data and look at a graphical display of it. We need to look at a graphical display of it and make sure that graphical display of my sample is roughly symmetric with no potential outliers. If we're smaller than 30, we can still be okay if that sample distribution looks that way. So what I did in my calculator, I'll go over it here so you can see I actually did the work already, is I went to stat and then I went to edit and I typed in all of my raw data. That's the first thing I did. The second thing I did is I wanted to graph this data. So I went to second stat plot. I turned my plot on and I chose the box and whisker plot that is going to show me potential outliers. Once I did that, I went to graph, and I did have to do a zoom stat here. This is what my sample data looks like. So looking at that box plot, yes, that is roughly symmetric, and there are no potential outliers that I see there. So what I did for the problem, to kind of make a very holistic problem here, is you just need a quick rough sketch of the graph you saw, okay? So you need some sort of graphical display. If there's no graphical display given, you gotta make one yourself, okay? So I made one and I said the box plot is roughly symmetric with no potential outliers. So now that accomplishes my goal on the third assumption. Because of all these things, I know I have some faith and confidence in the interval formula I'm going to use, okay? Everything's going to work itself out. So because these assumptions are now cleared, I can now name the type of problem I'm doing. I'm cleared to perform a one sample t interval. Another way you might see this is a one sample t interval for a population mu, which we defined up above. I'm just going to keep it to a one sample t interval is what we're doing. The final thing I did on my calculator is I went to stat and I hopped on over to test. And what I'm looking for is a one sample t interval. For this specific one, it's not listed as one sample t interval. The TI-84 calculator is listed as just a plain old t interval. I am using raw data. The data is in list 1. My confidence level is 95. If I would have had the summary stats here and they said, hey, the sample mean is this and the sample standard deviation is this, I would have gone to the stats tab and plugged in my sample mean, my sample standard deviation, sample size, and confidence. But they gave me the raw data, so I went to the data tab, typed it all in, and hit calculate. Okay, so it's going to spit out the interval for you, give you x bar, give you s, give you n, and that's how I started putting together my formula here. So x bar was, I rounded to 41.67, plus or minus, we'll come back to t star in a second. My standard deviation was 2.81, and my sample size is 12. I needed to find my critical t value. How we do that is we're going to use our t chart. First thing you're going to need to know is your degrees of freedom. So take your sample size and subtract it from 1. So my degrees of freedom is 11. So I know which row I'm on. The final thing I need to do is across the bottom is your confidence levels. We wanted a 95% confidence, so I went across to 95% confidence. You find where my degrees of freedom and my confidence meet up. And on my t table, that met up at 2.201 is my critical t value. With this formula, my calculator already computed it for us. It's a 39.88, 43.45. So this is the interval part of panic. And then finally, I need to wrap it up with some context. So what we say here is we are 95% confident the true population mean of number of sprinkles on donuts is between 39.88 and 43.45. So I believe, with 95% confidence, that the true average number of sprinkles that Tony's Donuts puts on their donuts, their sprinkled donuts, is between 39.88 and 43.45. Remember when we say 95% confidence, that means if I would have done this process over and over and over and repeated sampling, repeated getting intervals, sample, interval, 95% of all my intervals would actually capture the true population mean. So that was a quick run through a one sample t interval. Definitely be careful on that third assumption. That's really what's kind of hit on and kind of where you really need to pay attention. Everything else follows a pretty traditional confidence interval problem.